Definition. Perhaps the most distinguishing characteristic of mathematics is to reliance on logic. Explicit training in mathematical logic is essential to a mature understanding of mathematics. Familiarity with concepts of logic is also a prerequisite to studying a number of central areas of computer science, including databases, compilers, and complexity theory. We're going to see the table. The table has 4 columns. First column symbol, second column read, third column example, fourth column also read. We're going to read row by row. First row, we used to read the symbol as not. Example, P, that is called not P. We have to read P is not true, P is false. Second row, we used to read the symbol by and. Example, P and Q. We used to read P and Q, both P and Q are true. We used to read the symbol or. Example, P or Q. We used to read P or Q, P is true or Q is true, or both. We used to read the symbol implies. Example, P implies Q. We used to read if P, then Q. P only if Q. We used to read the symbol if and only if. Example, P if and only if Q. We used to read P by implies Q. P if and only if Q. Formal language and arguments. Formal language. Within that formal language, knowledge can be stated concisely and precisely. The process of reasoning from that knowledge can be made rigorous. Symbols and strings of symbols, well-formed formulas, theorems, arguments, specific cases, general rules or principles, inductive, deductive. Within that argument, some of these statements, the premises, are assumed to be true and serve as a basis for accepting another statement of the argument called the conclusion. Examples in arguments. Deductive argument. Alexandria is a port or a holiday resort. Alexandria is not a port, therefore Alexandria is a holiday resort. Inductive argument. Most students who did not do the tutorial questions will fail the exam. John did not do the tutorial questions, therefore John will fail the exam. Learning objectives. In this chapter, the user would learn the following aspects of mathematical logic: logic operators, truth tables, normal forms, propositional calculus, theory of inference and deduction, predicate calculus. Propositional logic. A proposition is a sentence that is either true or false but not both. In particular, it cannot be questioned. Simple types of statements are called propositions or treated as automatic building blocks for more complex statements. Examples: 2 plus 2 equal to 5, sin pi by 6 equal to 0.5. Basic propositions in the argument are: P represents Alexandria is a port, Q represents Alexandria is a resort. The rules of logic give precise meaning to the mathematical statements. These rules are used to distinguish between valid and invalid mathematical arguments. Besides the importance of logic in understanding the mathematical reasoning, logic has numerous applications to computer science. These rules are used in the design of computer circuits, the construction of computer programs, the verification of the correctness of programs, and in many other ways. Furthermore, software systems have been developed for constructing some but not all types of proofs automatically. Propositions. Our discussion begins with an introduction to the basic building block of logic propositions. A proposition is a declarative sentence, that is, a sentence that declares a fact that is either true or false but not both. Consider the following sentences. Number 1. What time is it? Number 2. Read this carefully. Number 3. X plus 1 equal to 2. Number 4. X plus y equal to z. Sentence 1 and 2 are not propositions because they are not declarative sentences. Sentence 3 and 4 are not propositions because they are neither true nor false. Note that each of sentences 3 and 4 can be turned into propositions if we assign values to the variable. The area of logic that deals with the propositions is called the propositional calculus or propositional logic. Many mathematical statements are constructed by combining one or more propositions. New propositions called compound propositions are formed from existing propositions using logical operators. Example: find the negation of proposition. Vandana's smartphone has at least 32 GB of memory, and express this in simple English. Solution: the negation is: it is not the case that Vandana's smartphone has at least 32 GB of memory. This negation can also be expressed as Vandana's smartphone does not have at least 32 GB of memory, or even more simply as Vandana's smartphone has less than 32 GB of memory. Table displays the truth table for the negation of a proposition P. This table has a row for each of the two possible truth values for a proposition P. Each row shows the truth value of negation P corresponding to the truth value of P for this row. Table: the truth table for the negation of a proposition. Table has two columns. P, negation of P. P represents T and F. Negation of P represents F and T. Conjunction: let P and Q be propositions. The conjunction of P and Q, denoted by P and Q, is the proposition P and Q. The conjunction P and Q is true when both P and Q are true and is false otherwise. Table: the truth table for the conjunction of two propositions. Table has three columns: P, Q, then the third column is P and Q. We're going to see row by row. First row: P represents T, Q represents T, then P and Q is T. Second row: T represents P, Q represents F, then P and Q represents F. Third row: P represents F, Q represents T, then P and Q is F. Fourth row: P represents F, Q represents F, then P and Q is F. This table has a row for each of the four possible combinations of truth values of P and Q. The four rows correspond to the pairs of truth values T, 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 F, F, T, F, F, where the first truth value in the pair is the truth value of P and the second truth value is the truth value of Q. Note that in logic, the word but sometimes is used instead of, and in a conjunction. For example, the statement "the sun is shining but it is raining" in another way of saying "the sun is shining and it is raining." Disjunction: let P and Q be propositions. The disjunction of P and Q, denoted by P or Q, is the proposition P or Q. The disjunction P or Q is false when both P and Q are false and is true otherwise. The truth table for the disjunction of two propositions. Table has three columns: P, Q, and P or Q. We're going to read row by row. P represents T, then Q represents T, then P or Q is T. Second row: P represents T, Q represents F, then P or Q is T. Third row: P represents F, Q represents T, then P or Q is T. Fourth row: P represents F, Q represents F, then P or Q is F. Conditional statements: let P and Q be propositions. The conditional statement P implies Q is the proposition if P, then Q. The conditional statement P implies Q is false when P is true and Q is false and true otherwise. In the conditional statement P implies Q, P is called the hypothesis or antecedent or premise, and Q is called the conclusion or consequence. The truth table for the conditional statement P implies Q. Now we're going to see the table. P, Q, and P implies Q. P represents T, Q represents T, P implies Q is T. Second row: P represents T, Q represents F, then P implies Q represents F. Third row: P represents F, Q represents T, then P implies Q represents T. Fourth row, P represents F, Q represents F, then P implies Q represents T. The statement P implies Q is called a conditional statement because P implies Q asserts that Q is true on the condition that P holds. A conditional statement is also called an implication. The truth table for the conditional statement P implies Q is shown in table. Note that the statement P implies Q is true when both P and Q are true and when P is false, no matter what truth value Q has. Because conditional statements play such an essential role in mathematical reasoning, a variety of terminology is used to express P implies Q. You will encounter most, if not all, of the following ways to express this conditional statement. If P, then Q. P implies Q. If P, Q. P only if Q. P is sufficient for Q. A sufficient condition for Q is P. Q if P. Q whenever P. Q when P. Q is necessary for P. A necessary condition for P is Q. Q follows from P. Q unless negation P. Biconditionals. Let P and Q be propositions. The biconditional statement P if and only if Q is the proposition P if and only if Q. The biconditional statement P if and only if Q is true when P and Q have the same truth values and is false otherwise. Biconditional statements are also called by implications. The truth table for the biconditional P if and only if Q. Table has 3 columns P, Q and P if and only if Q. We are going to see the table row by row. First row, P represents T, Q represents T. Then P if and only if Q is T. Second row, P represents T, Q represents F. Then P if and only if Q is F. Third row, P represents F, Q represents T. Then P if and only if Q is F. Fourth row, P represents F, Q represents F. Then P if and only if Q represents T. The truth table for P if and only if Q is shown in table. Note that the statement P if and only if Q is true when both the conditional statements P implies Q and Q implies P are true and is false otherwise. That is why we use the words if and only if to express this logical connective, and why it is symbolically written by combining the symbols implies and implies. There are some other common ways to express P if and only if Q. P is necessary and sufficient for Q. If P, then Q, and conversely, P if and only if Q. The last way of expressing the biconditional statement P if and only if Q uses the abbreviation if and only if for if and only if. Note that P if and only if Q has exactly the same truth value as P implies Q and Q implies P. Precedence of logical operators. Generally, we use parentheses to specify the order in which logical operators in a compound proposition are to be applied. For instance, P or Q and negation of or is the conjunction of P or Q and negation or. General rule of precedence is that the conjunction operator takes precedence over the disjunction operator, so that P and Q or R means P and Q or R rather than P and Q or R. It is an accepted rule that the conditional and biconditional operators implies and if and only if have lower precedence than the conjunction and disjunction operators or and. Consequently, P or Q implies or is the same as P or Q implies or. We will use parentheses when the order of the conditional operator and biconditional operator is at issue, although the conditional operator has precedence over the biconditional operator. Table displays the precedence level of the logical operators. Negation and or implies and if and only if. The precedence of logical operators. Table has 2 columns, operator precedence. Negation represents 1 and represents 2 or represents 3. Implies represents 4 if and only if represents 5. Predicate calculus. A predicate is a sentence that contains variables, and when the variables are substituted by numbers or actual objects, it becomes a proposition. Predicate calculus, on the other hand, is analogous to algebra, which is more complex than arithmetic, but it requires the knowledge of arithmetic. Predicates define relationships between any number of entities using qualifiers. For all, for every, there exist. Examples: x greater than 4, a square plus b square equal to c square. Extension of propositional logic. A predicate is just a property. Let p of x be the property. If x is a triangle, then sum of its internal angles is 180 degree. In predicate logic, for every x into p of x, for every x such that x is a triangle, the sum of the internal angles of x is 180 degree. Examples: let p of x be the property. X is an integer and x square equal to 4. Then there exists x into p of x. There exists x such that x is an integer and x square equal to 4. Predicates. A predicate is a statement that contains a variable such that for any specific values of the variable, the statement is a proposition. Usually, the allowed values of the variable will come from a specific set, sometimes called the universe of the variable. This will be either explicitly mentioned or clear from context. A simple example of a predicate is x2 for x2r. Clearly, for any real value of x, the statement is either true or false. A predicate may have more than one variable, in which case a speak of predicates in 2 variables, 3 variables, and so on, denoted as q of x, y, s of x, y, z, etc. Propositional functions. A statement of the form p of x1, x2, etc. xn is the value of the propositional function p. Here, x1, x2, etc. xn is an n-tuple and p is a predicate. Evaluates to true or false. Takes one or more arguments. Expresses a predicate involving the arguments. Becomes a proposition when values are assigned to the arguments. Example: let q of x, y, z denote the statement x square plus y square equal to z square. What is the truth value of q of 3, 4, 5? What is the truth value of q of 2, 2, 3? How many values of x, y, z make the predicate true? Since 3 square plus 4 square equal to 25 equal to 5 square. Q of 3, 4, 5 is true. Since 2 square plus 2 square equal to 8 equal to 3 square not equal to 9. Q of 2, 2, 3 is false. There are finitely many values for x, y, z that make this propositional function true. Universe of discourse. Universe of discourse is the set of all things we wish to talk about, that is, the set of all objects that we can sensibly assign to a variable in a propositional function. Consider the example. Let q of x, y, z denote the statement x square plus y square equal to z square. What is the truth value of q of 3, 4, 5? What is the truth value of q of 2, 2, 3? How many values of x, y, z make the predicate true? Does it make sense to assign to x the value blue? What would be the universe of discourse for the propositional function p of x equal to? The test will be x on the 23rd b. Moreover, each variable in an n-tuple may have a different universe of discourse. Let p of r, g, b, c equal to the RGB value of the color C is R, G, B. For example, P of 255, 0, 0, red, is true while P of 0, 0, 255, green is false. What are the universes of discourse for R, G, B, C? Quantifiers. A predicate makes a proposition when we assign it fixed values. However, another way to make a predicate into a proposition is to quantify it. That is, the predicate is true or false for all possible values in the universe of discourse or for some values in the universe of discourse. We form propositions from predicates by assigning values to the variables or by quantification. Since quantification can be done with the two quantifiers, the universal quantifier, the existential quantifier, and uniqueness quantifier. Universal quantifier, 8 read for all or for every. Existential quantifier, 9 read, there exist. Uniqueness quantifier, exclamatory read, unique. Given a predicate in more than one variable, we can quantify each or some of the variable. For example, the statement for every real x and y, it holds that x square minus y square equal to x minus y into x plus y can be formalized as for every x comma y belongs to R, x square minus y square equal to x minus y into x plus y. Somewhat more interestingly, the statement there is no greatest integer might be formulated as for every n belongs to z belongs to m belongs to z, m greater than n. Universal quantifiers. Universal quantification of a predicate p of x is the proposition p of x is true for all values of x in the universe of discourse. If the universe of discourse is finite, say n1, n2, etc., nk, then the universal quantifier is simply the conjunction of all elements. For every x into p of x, if and only if p of n1 and p of n2 and etc. and p of nk. Let p of x be the predicate. X must take a discrete mathematics course, and let q of x be the predicate. X is a computer science student. The universe of discourse for both p of x and q of x is R. UNL student express the statement every computer science student must take a discrete mathematics course. For every x into q of x implies p of x. Express the statement everybody must take a discrete mathematics course or be a computer science student. For every x into q of x or p of x. Given a proposition p, the negation of p is the proposition p is false. It is true if p is false and false if p is true. The negation of p is denoted by negation of p. Read as not p. If we know the meaning of p, such as when p stands for it will rain tomorrow, the proposition not p can be started more naturally than not p, as in it will not rain tomorrow. If the universe of discourse is finite, say n1, n2, etc. up to nk, then the universal quantifier is simply the conjunction of all elements. For every x into p of x, if and only if p of n1 and p of n2 and etc. and p of nk. P not p. P represents true, false. Not p represents false, true. Negations. A truth table simply lists the truth values of particular statements in all possible cases. Something interesting can be observed when we consider the truth values of q, which can be obtained by using the above table once with p, if and only if q, once with p equal to not q. We see that the statements q and q have the same truth values. In this case, we say that the two statements are equivalent and write Q, Q. If A, B, we can freely use B in the place of A or A instead of B. In our logical derivations, negation gets really interesting when the negated proposition is quantified. Then we can assert that not for every x belongs to A, P of x, if and only for every x belongs to A, not P of x. Not for every x belongs to A, P of x if and only if for every x belongs to A, not P of x. These can be interpreted as the claim that if P of x is not true for all x belongs to A, then it is false for some x belongs to A and vice versa, and the claim that if P of x is not false for any x belongs to A, then it is true for all x belongs to A and vice versa. What this means in particular is that if we want to disprove a statement that asserts something for all x belongs to A, it is sufficient to demonstrate one such x for which the statement does not hold. On the other hand, if we need to disprove a statement that asserts the existence of an x belongs to A with a certain property, we actually need to show that for all such x this property does not hold. Table represents Q, not Q, Q. Q represents true, false. Not Q represents false, true. Q represents true, false. Nested quantifier. The two quantifiers are nested if one is within the scope of the other. The sum of two positive numbers is positive. For every x, for every y, x greater than 0 and y greater than 0 implies x plus y greater than 0. Every number has an additive inverse. For every x, there exists y, x plus y equal to 0. There is a number such that this number times any other number results in 0. There exists y for every x, xy equal to 0. There exist two negative numbers that add up to minus 3. There exists x, there exists y, x less than 0 and y less than 0, and x plus y equal to minus 3. Table represents three columns. Statement, when true, when false. We read row by row. For every x, for every y, p of x comma y. For every y, for every x, p of x comma y. P of x comma y is true for every pair x comma y. There is a pair x comma y for which p of x comma y is false. Second row. For every x there exists y, p of x comma y. For every x there is a y for which p of x comma y is true. There is an x such that p of x comma y is false for every y. Third row. There exists x for every y, p of x comma y. There is an x for which p of x comma y is true for every y. For every x there is a y for which p of x comma y is false. Fourth row. There exists x, there exists y, p of x comma y, there exists y, there exists x, p of x comma y. There is a pair x comma y for which p of x comma y is true. P of x comma y is false for every pair x comma y. Existential quantifier. The existential quantification of a predicate p of x is the proposition. There exists an x in the universe of discourse such that p of x is true. It is denoted by there exists x into p of x. Again, if the universe of the discourse is finite, n1, n2, etc. nk, then the existential quantifier is simply the distinction of all elements. There exists x into p of x if and only if P of n1, P of n2, etc. P of nk. Let P of x comma y denote the statement x plus y equal to 5. What is the expression? There exists x, there exists y, P of nk. Mean. What universe S of discourse make it true? Express a statement that exists a real solution to ax square plus bx minus c equal to 0. Let P of x be the statement x equal to minus b plus or minus P of b square minus 4ac divided by 2a, but the universe of discourse for x is the set of reals. Note here that a, b, c are all fixed constants. What is the truth value of there exists x into P of x? Answer: it is false. For any real numbers such that b square less than 4ac, there will only be complex solutions for these cases. No such real number x can satisfy the predicate. Mixing quantifier. Existential and universal quantifiers can be used together to quantify a predicate statement. For example, for every x, there exists y, P of nk is perfectly valid. However, you must be careful. It must be read left to right. For example, for every x, there exists y, P of x comma y is not equivalent to there exists y for every x, P of x comma y. This ordering is important. For example, for every x, there exists y, loves x comma y. Everybody loves somebody. There exists y, for every x loves x comma y, there is someone loved by everyone. Those expressions do not mean the same thing. Note that there exists y for every x into P of x comma y factorial. For every x there exists y, P of x comma y, but the converse does not hold. However, you can commute similar quantifiers. There exists x, there exists y, P of x comma y is equivalent to there exists y, there exists x, P of x comma y, which is why our shorthand was valid. Express in predicate logic the statement that there are an infinite number of integers. Express in predicate logic the statement that there are an infinite number of integers. Let P of x comma y be the statement that x less than y. Let the universe of discourse be the integers z. The table shows the truth values. Table has 3 columns. Statement, true when, false when. We're going to read row by row. For every x, for every y, P of x comma y. P of x comma y is true for every pair x comma y. There is at least one pair x comma y for which P of x comma y is false. Second row. For every x, there exists y, P of x comma y. For every x, there is a y for which P of x comma y is true. There is an x for which P of x comma y is false for every y. Third row. There exists x for every y, P of x comma y. There is an x for which P of x comma y is true for every y. For every x, there is a y for which P of x comma y is false. Fourth row. There exists x, there exists y, P of x comma y. There is at least one pair x comma y for which P of x comma y is true. P of x comma y is false for every pair x comma y. Example. Express the statement there is a number x such that when it is added to any number, the result is that number, and if it is multiplied by any number, the result is x as a logical expression. Solution. Let P of x comma y be the expression x plus y equal to y. Let Q of x comma y be the expression xy equal to x. Example, is there a multiplicative inverse law over the non-zero integers? That is, for every integer x, does there exist a y such that xy equal to 1? This is false, since we can find a counter example. Take any integer, say 5, and multiply it with another integer y. If the statement held, then phi equal to 1 by y, but for any non-zero integer y, comma, modulus of 1 by y implies 1. Binding variables. When a quantifier is used on a variable x, we say that x is bound. If no quantifier is used on a variable in a predicate statement, it is called free. A statement is called a well-formed formula when all variables are properly quantified. In the expression, there exists x, y for every z, p of x, y, z, c. The scope of the existential quantifier is x, y. The scope of the universal quantifier is just z, and c has no scope since it is free. Lemma. Let p of x be a predicate, then the following hold. Not there exists x, p of x for every x, not p of x. Not for every x, p of x, there exists x, not p of x. This is essentially a quantified version of De Morgan's law. In fact, the universe of discourse is finite. It is exactly De Morgan's law. Proposition equivalence. Proposition equivalence feature three terminologies. They are contradiction, tautology, contingency. A compound proposition that is always true, no matter what the truth values of the propositions that occur in it, is called a tautology. A compound proposition that is always false, no matter what the truth values of the propositions that occur in it, is called a contradiction. A compound proposition that is neither a tautology nor a contradiction is called a contingency. Boolean operators. Boolean operators were unary and binary. Some of the Boolean operators are tabulated. Negation operator is a unitary operator. Operators like conjunction, disjunction, exclusive, or implication, biconditional were binary operators. The table shows 4 columns. Formal name, nickname, arity, symbol. Negation operator. Not, unary, symbol represents not. Conjunction operator. And, binary, symbol represents and. Disjunction operator. Or, binary, symbol represents or. Exclusive or operator. The nickname is called XOR. We used to call XOR. Binary. The symbol is called XOR. Implication operator. Implies. Binary. Symbol represents implication operator. We used to call the symbol as implies. Biconditional operator. IFF. Binary. The symbol represents if and only if. We used to call IFF as if and only if. Biconditionals. Let P and Q be propositions. The biconditional statements P if and only if Q is the proposition, P if and only if Q. These are also called bi-implications. Table has 3 columns. First column P, second column Q, third column P if and only if Q. First row P represents F, Q represents F, then P if and only if Q represents T. Second row P represents F, Q represents T, then P if and only if Q represents F. Third row P represents T, Q represents F, then P if and only if Q represents F. Fourth row P represents T, Q represents T, then P if and only if Q represents T. Two propositions are called equivalent when they have the same truth table. The contrapositive is equivalent to the original implication. The converse and inverse are equivalent to each other. The inverse is not equivalent to the original. Law of excluded middle. Tautology is called the law of excluded middle. Is a direct consequence of our basic assumption that a proposition is a statement that is neither true or false. Aristotelian logic might be described as a two-valued logic, and it is the logical basis for most of the theory of modern mathematics, at least as it has developed in Western culture. There is, however, a consistent logical system known as constructivist or intuitionistic logic, which does not assume the law of excluded middle. This results in a three-valued logic in which one allows for a third possibility, namely other. In this system, proving that a statement is not true is not the same as proving that it is false, so that indirect proofs, which we shall soon discuss, would not be valid. P implies Q and Q implies P is logically equivalent to P if and only if Q. The truth values of both propositions are identical. The table shows 6 columns. First column has P, second column Q, third column P implies Q, fourth column Q implies P, fifth column P implies Q and Q implies P, sixth column P if and only if Q. We're going to see the table row by row. First row T, 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 T and then T. Second row T, F, F, T, F, F. Third row F, T, T, F, F, F. Fourth row F, F, T, 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 then T. Examine every possible case in which the statement P implies Q and Q implies P may not have the same truth value as P if and only if Q. Case 1. Suppose P implies Q and Q implies P is false and P if and only if Q is true. There are two possible cases where P implies Q and Q implies P is false. Namely, P implies Q is false or Q implies P is false, note that this covers the possibility both are false since we use the inclusive or on logic. A. Assume P implies Q is false, then P is true and Q is false. But if this is the case, the P if and only if Q is false. B. Assume Q implies P is false, then Q is true and P is false. But if this is the case, the P if and only if Q is false. Case 2. Suppose P implies Q and Q implies P is true and P if and only if Q is false. If the latter is false, the P and Q do not have the same truth value and there are two possible ways this may occur that we address below. A. Assume P is true and Q is false, then P implies Q is false, so the conjunction also must be false. B. Assume P is false and Q is true, then Q implies P is false, so the conjunction is also false. Logical equivalences. Some of the important logical equivalences were identity law, P and T, if and only if P, P or F, if and only if P, domination law, P or T, if and only if T, P and F, if and only if F, idempotent law, P or P, if and only if P, P and P, if and only if P, double negation law, P dash whole dash, if and only if P. Some of the important logical equivalences were commutative laws, P or Q, if and only if Q or P, P and Q, if and only if Q and P. Associative law, P or Q or if and only if P or Q or P and Q and if and only if P and Q and distributive law, P or Q and if and only if P or Q and P or P and Q or if and only if P and Q or P and absorption law, P and P or Q, if and only if P, P or P and Q, if and only if P. Some of the important logical equivalences were implication law, P implies Q, if and only if P dash or Q, contrapositive law, P implies Q, if and only if Q dash implies P dash, tautology, P or P dash, if and only if T, contradiction, P and P dash, if and only if F, equivalence, P implies Q and Q implies P, if and only if P, if and only if Q. Implication, the proposition or implies the proposition S and we write or implies S. If or implies S is a tautology, we say the proposition or implies the proposition S and write or implies S. If or implies S is a tautology, this is very similar to the ideas previously discussed reading the if and only if versus if and only if. We use or implies S to imply that the statement or implies S is true, while the statement or implies S alone does not imply any particular truth value. The symbol implies is often used in proofs as a shorthand for implies. Well-formed formula, WFF. A well-formed formula. Syntax of compound proposition. Any statement variable is a WFF. For any WFF, alpha, not alpha is a WFF. If alpha and beta are WFFs, then alpha union beta, comma, alpha union beta, alpha implies beta, and alpha if and only if beta are well-formed formulas, that is called WFFS. A finite string of symbols is WFF only when it is constructed by steps 1, 2 and 3. WFF, negation of P and Q, comma, P implies P or Q, comma, negation of P and Q. P implies Q and Q implies R if and only if P implies R, etc. Not WFF. Number 1. P implies Q implies and Q is not a WFF. Number 2. P implies Q, but P implies Q is a WFF, etc. Substitution instance. A WFF A is a substitution instance of another formula B if A is formed from B by substituting formulas for variables in B under condition that the same formula is substituted for the same variable each time that variable is occurred. B. P implies J and P, A, or implies S, implies J and or implies S. A substitution instance of a tautology is a tautology. Example: B, P or implies P, A, Q and or implies Q and R. Every compound proposition in the propositional variables P, Q, R, etc. is uniquely equivalent to a proposition that is formed by taking the disjunction of conjunctions of some combination of the variables P, Q, R, etc. or their negations. This is called the disjunctive normal form of a proposition. The disjunctive normal form of a compound proposition is a natural and useful choice for representing the proposition from among all equivalent forms, although that may not be the simplest representative. We will find this concept useful when we arrive at the module on Boolean algebra. Example: 1. P is true and Q is false. Solution: P and Q. 2. P is true and Q is false, or when P is true and Q is true. Solution: P and Q dash or P and Q. Constructing disjunctive normal forms. The disjunctive normal form for the proposition P implies Q. P implies Q is true when either P is true and Q is true, or P is false and Q is true, or P is false and Q is false. The disjunctive normal form is then P and Q, or P dash and Q, or P dash and Q dash. Now we're going to see the table. P, Q and P implies Q. Now we're going to read row by row. First row, P represents T, Q represents T, then P implies Q represents T. Second row, P represents T, Q represents F, then P implies Q represents F. Third row, P represents F, Q represents T, then P implies Q represents T. Fourth row, P represents F, Q represents F, then P implies Q represents T. Constructing disjunctive normal forms. The disjunctive normal form will be a disjunction of 3 conjunctions, one for each row in the truth table, that gives the truth value T for P implies Q and or dash. These rows have been boxed. In each conjunction, we will use P if the truth value of P in that row is T and P dash if the truth value of P is F, Q if the truth value of Q in that row is T, and Q dash if the truth value of Q is F, etc. The disjunctive normal form for P implies Q and or dash is then P and Q and or dash, or P dash and Q and or dash, or P dash and Q dash and or dash. Because each of these conjunctions is true only for the combination of truth values of P, Q and R found in the corresponding row, that is P and Q and R dash, as truth value T only for the combination of truth values in row 2, P dash and Q and R dash as a truth value T only for the combination of truth values in row 6, etc. Now we're going to see the table. First column as P, second column as Q, third column as R, fourth column as P implies Q, fifth column as not R, sixth column as P implies Q and not R. We're going to read row by row. First row, T, 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 F, F. Second row, T, T, F, T, T, T. Third row, T, F, T, F, F, F. Fourth row, F, T, 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 F, F. Fifth row, T, F, 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 T, F. Sixth row, F, T, F, T, T, T. Seventh row, F, F, T, T, F, F. Eighth row, F, F, T, T, T. Conjunctive normal form. The conjunctive normal form of a proposition is another canonical form that may occasionally be useful, but not to the same degree as the disjunctive normal form. The conjunctive normal form of a proposition is the equivalent form that consists of a conjunction of disjunctions. It is easily constructed indirectly using disjunctive normal forms by observing that if you negate a disjunctive normal form, you get a conjunctive normal form. For example, 3 applications of De Morgan's laws gives P and Q dash or P dash and Q dash if and only if P dash or Q and P or Q whole dash. Conclusion. In this chapter, the user have covered the following aspects of mathematical logic: logic operators, truth tables, normal forms, propositional calculus, theory of inference and deduction, predicate calculus.